Hey, and welcome back. We're talking about section 2.2 now, and we're talking about the circle. Every equation we're going to find out in chapter 2, different equations have different shapes associated with them. Like you may have already learned in 2.1, just plotting some graphs that when x is to the first and y is to the first, it always lines up to be a straight line, which is pretty neat when you think about it. Um, so what happens in 2.2 is when x is squared and y is squared, when both variables are squared, it works out to be a circle. So just kind of neat these patterns that we're going to see. So if it's just a regular x squared, positive 1x squared and 1y squared, or it could be other equal coefficients in front of it. But anytime this happens, equals a constant, a positive constant, on the end, it's going to shape out to be a circle. So we could plot some points. For example, if we had x squared plus y squared equals 9, we could come up with some t-table values, pick some numbers for x, plug in for x, solve for y. They're going to work out to just fall in this circular figure. Remember, graphing is always a picture of the solutions to your equation. So whenever you plot points on your graph, you get a picture of the solutions to this. One solution you may think of, just a nice one, is 0 and 3. 0 squared plus 3 squared does equal 9. Another one you might think of is 0 and negative 3. If that's negative 3 when it's squared, that also works. 3 and 0. Negative 3 and 0. Those are the only nice ones. There are other ones, like if I plug in x is 1, I'm going to get a solution, but it's not going to come out like a nice integer number, but it is still going to be a solution I can plot. These are the only nice ones. Let's go ahead and plot these and just see how that looks on the graph. 0, 3 would be right here. 0, negative 3, 3, 0, negative 3, 0. My graph's not perfectly calibrated, but when I circle those in, there it is. There, that does come out, and again, I would have to show you more points to really show you how you got all that around it, but just the general, it does work out to be this circle. Every little point along this curve is also a solution. So we could plug in x is 1, solve for y, and it's going to be over 1, up that far, down that far, and so on. Well, anyway, we're not really going to do it that way. We're generally just going to look at an equation and say, hey, I know that's a circle. The last number is the radius squared, which in this case would be 3 squared gives us 9. So the radius is going to be 3, and then I can just kind of draw that in. Now, if another example, if I have x squared plus y squared equals 16, another circle. It's going to be a circle centered at the origin again, and the radius is going to be 4. So again, we're just recognizing the pattern. We have x squared, y squared. It graphs to be a circle. Again, we could prove that if we really wanted to plot more points, but we're going to believe that is the formula given in the book on 2.2. X squared and y squared, when they're both positive and equal coefficients in front of it, always graphs to be a circle. If you have a positive number over here, that's the radius squared. So again, the radius is 4 this time. So out 4 from it, and draw that in. So again, if it's just x squared and y squared equals a number squared, that is centered starting at the origin and then go out the square root of that for the radius. Now, not all circles are centered at the origin. So this other formula you'll see in 2.2 in your book, it shows that sometimes it's offset. Sometimes your circle is over here in quadrant 1, or it's down here in quadrant 3. So it's offset from the origin. So if there is an offset, it will look like this, where H and K represent the centering or the offset of the circle. So notice it's still x squared and y squared. There's still a positive between it, and 1's in front here equals the radius squared. But you have this h and k, which moves your circle away from the origin for its centering. So notice that h and k change signs. If you got an x minus h, it's a positive h, and y minus k becomes a positive k. And that's where your centering is. And again, the number on the end is the radius squared, so r is the radius. So an example of that, maybe we have x minus 3 squared plus y plus 4 squared equals 16. This has the setup to be a circle. We suspect it because x is squared and y is squared, but we have these numbers here that offsets it from the centering, and the radius is going to be 4 in this case. So the center, or the offset, is positive 3, negative 4. Again, notice we're always changing the sign of what we see here in this parenthesis. And then we could graph that if requested. Over 3, down 4, say approximately there, and then the radius is 4, go out 4 places all around it, and you could draw your circle in. Another example, say we have x plus 1 squared, y minus 2 squared equals, let's do 14 this time, because it's not always just a perfect square there. It's just nice when it is. It's easier to graph if asked. But here our radius is the square root of 14, which we could do on our calculator to get a decimal approximation, but anyway, the radius is the square root of whatever that number is over there. Then the centering is, change the sign here, negative 1, positive 2. And then again, we can sketch that, start back 1 and up 2 is the center. The square root of 14 is going to be a little less than 4. It's going to be like 3.7 maybe, so we can estimate that, draw our circle in if needed. Most of the time it's just going to say list the center, list the radius. So we can leave it just like that. Well, not always is the circle in this nice format just ready to pick out the center and the radius. Sometimes we have to do a little algebra first. So I am on example, let's do example 3 in your book. Okay, so this one's not already set up in the formula form, so we will need to clean it up first to see where our center and radius is, but I still suspect it's a circle. One thing, it's in this section, but the other thing is I have a 1x squared and then a lesser x, and then a 1y squared, a lesser y, but you go by the biggest exponent, that's the degree 2, that's what clues me in, it's probably a circle. I've got x squared and a y squared, they're both positive. Then I've got some other terms, but I expect it'll work out to look like this circle formula. So what you do is collect your x terms together and leave a little space and kind of collect your y terms, and then any constant throw across the line, because that's where we get our radius, is from the constant part. Now I want to clean this up so it looks like the formula. I have an x minus a number squared. So that's completing the square, and that's something we learned in section 1.4 when we were talking about strategies for solving quadratics. If you complete the square, you can make it look like that. So what we do to complete the square, we need a 1 coefficient of our square term. Then we half the middle and square it. So half of 6 is 3. 3 squared is 9. We will be adding 9 to the left side, so we must add 9 to the right side to keep the balance. We're allowed to do that as long as we do it to both sides. Well, by adding in this half squared value, this makes this now look like that old factor. This will always factor. It factors into x minus 3 times x minus 3. You could FOIL it and show that it's so, but take a minute if you want to do that. See, it is equivalent. So we can just call that x minus 3 to the second. And then over here we can do the same thing to the y's, complete its square. Again, half the middle term is 5. 5 squared is 25. So adding 25 to the left, so you have to add 25 to the right, keeping that balance. That makes this also factorable. Again, it's always guaranteed to factor if you've half this and squared it. If you completed the square correctly, this is going to factor into a binomial squared. So it'll fit our formula pattern here. And then combine your like terms over here, negative 18, 9, 25. Combining those like terms, we get 16. And now it's ready to roll like our former problems. It's in center radius format. Changing the signs here, 3, -5, and the radius square root of 16 is 4, and then it could be graphed if requested. Okay, let's try that again. Okay, looking at example 4. Okay, so here's another example for our circle where I suspect it will graph out to be a circle. I've got an x squared and a y squared, and there's some lesser x's and y's, but we go by that biggest exponent is what drives the shape that I'm looking for. The largest exponent is 2, and 2, I suspect the circle. Also, they're equal coefficients, both positive. That's how circles are. So anyway, and also it's in the circle section. But I'm going to try to make it look like our circle formula. So I'm going to collect my x's. Okay, kind of have to rearrange here, but they are still on the left side, so don't change their signs, you know. And then the constant is already on the right side. Now, the thing is, you cannot complete the square unless you have a 1 coefficient on your square term. That's just the rule with that little procedure. So if you have a different number, we're going to have to divide everything by that. But luckily, the x squared and the y squared have the same coefficient, so that'll work for both. So we divide everything by that 2. And we hope it doesn't create fractions, but sometimes it does. And it did just a little bit. Now, completing the square like we did in the last example, we will half the middle term and square it. So half of 3 would be 1 1/2, and then squaring that, it's probably better to leave it as a fraction instead of a decimal. So 3 halves and then squared, that's 9/4. So I add 9/4 to each side. Then this is guaranteed to factor. It factors into the square roots. So that was 3/2 before it was squared. And this one's minus. Do the same thing for the y's. Half the middle term. So 5 half it is 5/2. Then square. Again, completing the square is half the middle term and then square it. So it squares top and bottom since it's a fraction. 25/4. So you do 25/4 to left and right. The y's now are factorable into y plus 5/2. And then we got to figure out what all of that is. I'd use my calculator, type all that in. I'm going to look in the book and see. Oh, it comes out to be 9 by some miracle. It all works out to a perfect integer number. Well, anyway, now it's in that nice format. We can tell the center is the opposite sign of what you see. So positive 3/2, negative 5/2. And the radius is always the square root of that last number. Square root of 9, 3. That's our vital information. Just another note about it, if you would do this process and add all the stuff over to the right side to keep the balance, and this number on the right, if it's 0, which could happen, you could just 0 out everything. If you get a 0, then you're just going to have a center but no distance to it. The square root of 0 is 0, so it's real, but it just has no distance, so it's just a point. And then on the other hand, if you would get a negative number, if this number, after you've completed the square and cleaned it up, if that number is negative, the square root of a negative is imaginary, so you would not get a circle. You'd get a non-existent figure. It would not graph to be a circle. So this number on the end has to be a positive number after it's cleaned up into our formula format. So you can take the square root of the last number as your radius, but it has to be positive to get the circle. If it's 0, it's just a point, and then if it's negative, it's just nothing. It's no graph.